My name is Norman Paul. I'm a lecturer in the Department of Computing, University of Surrey in the UK. Today I'm going to present to you Big Data in Healthcare, a computational perspective. Here's my brief background. I graduated from University of Science Malaysia, and then I went on to do a master in University Louis Pasteur in France, followed by a PhD in Switzerland. I obtained my PhD from École Polytechnique Fédérale de Lausanne. Since 2006, I have been with University of Surrey, taking different positions, such as research fellowship at the Center of Vision, Speech and Signal Processing, and at Clinical Informatics, um, where I did my study in healthcare. Since 2012, I'm a lecturer at the Department of Computing. All this while, I've been doing research in biometrics and machine learning. So healthcare and big data research are rather recent. Here is my research philosophy. On the left-hand side, we have applications which define the problems. And the problems can be in terms of volume, velocity, variety, and veracity. You can see a link there which explains more. Now, volume is the size of data. Velocity is the speed of the data that arrive into the data storage. Variety is the types and differences of information captured in the data, and veracity is the potential, the truthfulness of the data. So if the data are erroneous, um, then they need to be corrected for. There are also domain-specific problems like longitudinal. In the healthcare area, we're going to have a lot more longitudinal data that something that happened 10 years ago might affect your health today, for example. And there are also lots of confounders. One of the particular important example confounders are age and gender of the person. We know that as we get old, we get a lot of sicknesses, and then female tend to live slightly longer than male, and so this happens to all types of diseases. These two variables, in fact, are strong predictors of other diseases, but they themselves are not the cause of the disease, so they are called confounders. So on the left-hand side, we focus around on the practical aspect of the data, which is what we call big data. On the right-hand side, we have theories and algorithms developed by the statistics and machine learning communities. Taking the problems on the left and the theories on the right, theories and algorithms on the right, plus faster computers and ever-increasing memory, cheaper memory, then bonds a new field called data mining. It is about understanding, exploration, discovery of patterns and trends. It is also about data visualizations, about how do we look at data in a meaningful way to discover patterns. There are, of course, practical considerations such as software and hardware platform to enable all these elements to put together to process data and to solve practical problems. Now, I want to talk about information abstractions at different levels of granularities. On the left-hand side, we have codes or words or concepts, and in the middle we have patient records, and on the right-hand side we have extracted information and knowledge. And the idea is, of course, to extract usable knowledge. In machine learning terms, this means statistical models such as logistic regression and Cox regression, very much used in healthcare. But we also talk about estimating conditional probabilities such as the probability of a stroke given some observations. And to go from to the right-hand side, we typically rely on several tools. And the first one is information retrieval, where we associate words with documents. For example, in the Google search engine, this is what the Google search engine does. Now, from documents to knowledge, we use machine learning and data mining algorithms to achieve this. Healthcare is an important big data problem. To illustrate this, I draw a figure with three dimensions here. In the x-axis, we have the number of concepts. To give you an idea, um, the English words has 750,000 distinct concepts. In the SQL, we can deal at most with 700 variables. So these are the concepts dimensions. I want to explain particularly the clinical concepts uh, that are often adopted. In the UK, we use what's called a 5-byte red code, and it has 130,000 concepts. So one code would represent one disease or one specific type of disease. There's also another standard that's called SNOMED. It stands for Standardized Nomenclature of Medicine dash Clinical Terms. And this is an international standard that codify all the clinical concepts around the world. And the number of concepts is, of course, increasing day by day. The y-axis, we have the number of patients, or analogously number of objects or documents. We deal with a million patient records. Now, in a population level, we will have deal with several millions of patients. There are several big data sets available. QICKD is one that I work with. There are also UK Biobank, which capture the genomes of 500, half a million people in the UK. We also have the years dimensions. In the UK, GP clinics started to digitize their data since the 1990s, and there's also HASE, which is called Hospital Episode Statistics. These are hospital data that are available since 2005. Therefore, these three dimensions of the problem actually create a relatively new problem, hence requires new solutions. So the next question is, how do we process large amount of data? We can use more CPU, more RAM, more computer, faster computer, and these are we call hardware upgrade. Now, as a computer scientist or data engineer, we will focus on software upgrade. Now we can use the power of GPU, so we have to program differently. We do vectorization, for instance. We can design more efficient algorithms. And finally, we can design better data storage systems, such as using Hadoop and all other big data storage technologies. So how do we rate whether algorithm is good or not? I always use the following criteria. First, is it faster? Second, is it better? And third, is it cheaper? And finally, very importantly, does it improve our understanding? So if we have two algorithms, um, one uses the results, the other one explains the results. In this case, the second algorithm is potentially very useful, especially in the clinical domain. Here is a typical workflow of data analysis in a clinical study. The process begins by a clinician who enters his specification into the system. By relying on a clinical ontology or data dictionary, the system extracts the variables of interest. The variables of interest are represented as a sparse matrix. A sparse matrix is an example of sparse matrix is shown here, where the number of the rows are the number of patients, and the columns are the variables of interest. So one column is one variable. The system then selects the feature and then combine the columns of variables to form a denser matrix, which is then subject to data modeling, the result of which is a statistical model. The model are used in two ways. First, for analysis and reporting, and second, for clinical decision support. By far, analysis and reporting is the main use of data analysis in clinical research. The, the future trend, of course, is to build clinical decision supports from the model derived from the data. But that's the long-term objective. The process then repeats itself in iterations. My research revolves around these few issues. First, how to create an easy-to-use specification. Second, how to automate the data cleaning process. We know that 80% of the time spent on data analysis is actually used to clean the data or to explore the data. How do we extract data faster? How do we automate the feature selection process? How do we improve the accuracy of data modeling? I'd like to summarize what we have discussed so far. Big data of technologies offers plenty of opportunity in healthcare. We can contribute to different aspects, addressing questions such as how to deal with ever increasing size of the data, how to accelerate the knowledge extraction process, how to design faster or better algorithms, and finally, how do we improve the productivity of clinicians so that they can do their work faster and better.